Click on that. Um, okay, this has been an embarrassing silence, YouTube. I'm just recap. I've just been giving examples of like addition and multiplication and substitution of monoids. That's to say, I was about to explain that the ingredients for a monoid is a type to start with. We've had number and we've had formula. And you also need an operation, which in the abstract, I'm just going to write as this symbol. But concretely, we've seen it be plus, we've seen it be times, we've seen it be substitute. And then you need to give that operation a neutral element. And you need to prove that the neutral element really is neutral. So that's these two things. And you have to prove that the operator is associative. And then no matter what the monoid is, you have that method for combining any number of things to get one thing. If you're starting with no things, you use the neutral element. If you're starting with one thing, you use the thing. If you've got two or more things, you pick any two neighbors, you combine them with the operation until, and you keep going until you've just got one thing left. And the associative law tells you that it didn't matter which neighbors you pick, you're going to get the same answer anyway. Okay, that's that stuff there. So what I want to show you, and I might stop sharing my screen, and I might instead pin this screen and switch to the document camera. So
sadly it's on the other side,
but give me document camera everywhere. Fabulous. Okay, so I'm going to draw with my exciting collection of Sharpies a picture of a calculation, which is going to look like this. Maybe I'll do and I'm going to pick a color and I'm going to write some numbers in. Right. In this picture, the little blob with nothing coming off to the top that just has an output, that's going to stand for the neutral element. And the things with two inputs and one output, that's our operation. And if we pick, and I've put some actual data in these boxes, and if we pick that we're going to do, that the operation, the monoid we're working with is plus, then I can fill in what's on all the wires. So the neutral element's coming out of this blob, so there's a 0 here. And when I combine 0 and 4, I get 4. When I combine 1 and 2, I get 3. And when I combine 3 and 4, I get 7. And when I combine 3 and 7, out comes 10. Okay? So this is just a picture of a computation adding up some stuff. So one thing about being a monoid is that the actual wiring internally to the picture doesn't matter a damn. What's important is the sequence of the numbers in the boxes. 1, 2, 3, 4. That's what we're adding up. The strategy we use to wire them all together doesn't matter. So this is good information, right? Knowing about structure like monoids means knowing about stuff that doesn't matter. And if it doesn't matter, that means you can do what you want. This is good news. But the other thing about this picture is that at every node in this diagram, we learn a true fact about adding. So here we have the neutral element is 0. Here we have 0 plus 4 is 4. Here we have 3 plus 4 is 7, and so on. So this picture, as well as drawing a calculation, tells us a bunch of true facts about adding. Now, there are some very special operations, right? There are lots of things you can do to numbers, but some of them are special. For example, suppose I grab a different color and systematically multiply all the numbers in the picture by 9. Right? So this becomes 9, 18, 27, 36. This is 0. This is 36. This is 63. This is 27. And this is 90. Right. All I've done is the same function multiplying by 9 to all the data in the picture. But do you agree that if we read the picture as trying to tell us stuff about adding, it still tells us true facts about adding? It is true that 9 plus 18 is 27, and so on. We've done an operation to the data in the picture that preserves all the true facts that the picture was telling us. So this is a really well-behaved operation that relates adding to adding, not just numbers to numbers. So that's the point, is that multiplying by a chosen constant, in this case 9, isn't just an operation that turns numbers into numbers. It's an operation that turns adding into adding. It connects one monoid with, as it happens, the same monoid. And it obeys. So that makes it what we call a monoid map. Okay, so let me go back to sharing my screen on Zoom and go back to laptop in the room. Right. So what's a monoid map? So let's say we have two monoids. I've just called them the type 1, op1, new 1, type 2, op2, new 2. A monoid map is a function that works from maps values in type 1 to values in type 2 that behaves in a very special way. It turns the neutral element of monoid 1 into the neutral element of monoid 2. And if you do op1, so if you do a calculation in monoid 1 and then send its answer with f to monoid 2, you send the output to monoid 2, you get the same answer as if you send the inputs to monoid 2 before you do the calculation and you use monoid 2 to combine them instead. So that's to say, that's the same thing as saying that it preserves the truths in the picture. And this is an example of something your teachers, I don't know, did this get called the distributive law when you were at school? The distributive law, definite article. Ho, ho, ho. Imagine thinking there's only one of them. And possibly you weren't told that it's of a piece with noticing that a times 0 is 0. So multiplication by a takes the neutral element of adding to the neutral element of adding. And it doesn't matter whether you multiply the output of adding or multiply the inputs of adding, you get the same answer. Okay? So these are things that were disconnected in school mathematics that I'm trying to draw into one place, so that as you get older and your brain cells fade with time and alcohol abuse, you have fewer things to remember, but you still know the same amount of stuff. And okay, so we have established that multiplication by a constant is a monoid map from adding to adding. And my question is, for Clemens, are there any monoid maps from adding to adding that are not multiplying by something? And so what I've done here, set Clemens up, is I've built an operation, a mystery function from number to number. I'm not going to define it, but I am going to promise you that it obeys the rules for being a monoid map. And I'm going to see if Clemens can prove this result, that whatever it does with B is B times whatever it does with 1. So that's the question. If you're trying to define a monoid map, right, not just any old function, but one that is well behaved like this, what choices do you have? Turns out,
not many.
Not many.
Okay, so here we assumed already indeed that it's a monoid map in the 2 lines above. And now we want to actually prove this. And how do we do this? Obviously, we start by inductively B because...
Yes, yeah, multiplication stuck on its second input. Yeah.
And then immediately we do a from B to see what are the cases we have to deal with. How do you do this again?
I'll do that bit.
There's a smart way of doing what I'm doing normally manually. Okay, good. Excellent. So now we are stuck here with proving something about mystery, namely that mystery of the successor of X is equal to mystery of 1 times the successor of X. And inductively, we know that this is true for X, this equation. So somehow we want to use this induction hypothesis.
Probably want to do a test first, just to
Indeed, you're good.
Get some computation happening.
I would have really had some trouble without the test. So test is always to get some computation running as far as possible. And now we are at home. So test helped me a bit. And so if you look here on the right-hand side, there's something called mystery of successor of Z times X, which is half of the inductive hypothesis. So why not stick the inductive hypothesis in the root by?
Yeah, it's by root, not
by root, indeed.
Yeah.
Very good.
And then in
Parenthesis, and then we do misery. I'm gonna rename the function into misery in the process.
Yes.
So it's the mystery stays, but we also do now the induction here. So what is it? Mystery of X. Good. And now this fine, I hope.
Yeah.
So basically, we just kind of ask that here it's a good moment to use the induction hypothesis, but we actually have to ask to using it under the plus. Because we have the plus, the first part is the same. The second part is, command U, no, command.
Other people's keyboards are a nightmare.
Indeed.
So by root splits a difficult equational problem into 2 easier ones by putting a stepping stone in the middle.
Yes, and so it's not entirely clear because after writing by root, we only got one equation because the other one was obvious to ask to solve, so to speak.
Yes, and that's often the case. If you've chosen a sensible root, it's usually the case that one of the equations is easy, possibly so easy it's obvious, and the other one still takes work. So here we're starting from the right-hand side, spotting an opportunity to use the induction hypothesis and taking a step towards the left.
I kept the highlight under the carpet, obviously. So after writing on the plus, we got the proven here.
Yes.
Which means that this is true,
right,
provided that the things further up actually are.
So we don't. So the reason we don't get all the way out to proven at the top there is because I didn't prove that mystery was a monoid map. But you can see in the local proof that we're doing, ask is not complaining about stuff it doesn't know anymore. So we're there. We've shown that the only possible monoid maps from adding to adding are multiplying by something. And the reason for that is that you can take any number, chop it up as a sum of ones, and then you know that whatever you do, that you know that you're free to do the monoid map to the inputs. So you transform all those ones, and then you add them up afterwards. So the only thing you can possibly do in a monoid map from adding to adding is multiply by whatever it is you send one to. That's your only choice. Where do you send one? Okay, so this is good. You know, the picture is that when you've got some notion of the good behavior you're looking for, problems get easier rather than harder because you've only got you've got less freedom to get things wrong. So this is pretty cool. But we're going to show you first on paper, so I better stop sharing. Yes.
Yes.
So
Let's go back.
let me put this back to sharing.
I don't know whether I can use this microphone or probably not. No.
This is the right thing. Right. So, yes, it's important that we develop reading comprehension. So this whole thing here is the sum of two things. The first thing says mystery, and then SZ means one. Yeah, so when I write two things beside each other, they're just next to each other, like mystery one, what I'm saying is that the thing on the left is a function, and the thing on the right is its input. And the whole thing means whatever comes out. So mystery one means whatever comes out of mystery when you put one in. Is that making sense? Okay. Right, now I want to go back to document camera and make sure laptop is pointing at the picture. Right. Oh, I want a different color. Right. So you might have learned some laws about exponentiation in high school, and not recognized them for what they were. So here's my picture. Remember, it tells, it's full of true facts about adding. Now I'm going to do something else to all of the data in the picture. Because I'm a computer scientist, I'm going to raise all the numbers. I'm going to take 2 to the power of all the numbers. Okay? So let's do that. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 3 is 8. 2 to the 0 is 1. 2 to the 4 is 16. 2 to the 4 is 16. 2 to the 7 is 128. And 2 to the 10 is 1024. I just know that, and by the time you've been here for another few weeks, you'll just know that too. My pink picture no longer tells true facts about adding, but it does tell true facts about multiplication. So that's to say, 2 to the power is also a monoid map, not from adding to adding, but from adding to multiplication. And we do the same operation to all of the data, and we get true facts. We turn facts about adding into facts about multiplying. So you may have been taught at school that a to the 0 is 1 and a to the b plus c is a to the b times a to the c. And these two separate facts are just one fact, that exponentiation is a monoid map from adding to multiplication. And guess what? Logarithm is a monoid map the other way. You were taught laws of logarithms, perhaps. Anyway, so that's another example. And let's go back to the laptop and get Electric Clemens to build this machinery.
Let's see what happens.
Yes.
It can only go wrong.
Yeah. There's a good way to do this and a bad way. I'll if you've forgotten which way round is the bad way,
I think I know which one is the good one.
we'll fix it.
So wait a second. So first of all, we have to define that function, right? To the exponentiation by n.
Yeah, you don't want an equal sign.
Indeed, I want to have an inductively.
Yeah. You
Sorry.
need to say on what?
Of course. But how do I go back? Control X.
Control X. Control X U. Yeah.
Indeed. Sorry about this. Now we go. Now we do a from n. And now we are finally in the cases. So power 2 to the 0 is, as we just again heard, equal to SZ.
Yeah.
And then powers 2 to the x plus 1 is the more tricky. Here we have a choice, and there are many. There are bad choices, but as far as I know, there's a good choice, and the good choice is just doing 2 times.
Yeah, you need more parentheses.
Like this.
Yeah.
So we need a 2, and then we do power 2 of x. Do we need like this?
Yeah.
Good.
It's tab.
Yes. Good. So the easy bit is done, defining the function. Now we have to prove a few things to it. Right. So this is the main case. So this is 2 to the x plus 1 equals 2 times 2 to the x.
Yeah. Okay. So you get 2 to the x, and then you double it one more time.
Yes. Okay, sorry. So now we need to prove the first thing. Let's just do a test, I guess.
Yes.
Because that's just the first line of the definition. So that's easy. Maybe it goes like this. Further. No, but now we need to prove a bit of things. And I guess we are stuck somewhere because we're stuck.
Yeah.
Where are we stuck, in fact?
Yeah, well, where are we stuck? Power 2 is stuck because a plus b is stuck.
And a is then the stucker.
Yes.
But on the other side,
yeah, but on the other side,
we actually
we're stuck on B, but you know, you'll get some action somewhere if you hit A.
Okay,
That's
so
a dodgy one. This is our first example where
you stuck
where there's one vote for A and one vote for B, but you know, even if you make B unstuck, it's not going to help. Or maybe it is.
I didn't try, right?
There's more than one way to skin a cat. Right.
I'll do that. You do the magic. It's mainly the alt keys on a different. Yes. Yeah. Good. Right. So now we have to prove indeed that 2 to the x plus 1 plus b is equal to 2 to the x plus 1 times 2 to the b.
You'll be wanting a test then.
Indeed. So now, as almost always at this moment, you have to do a test to do some computation. And so now we are very much similar to the previous case in some ways, because if you look on this side after the computation, This is half of the induction hypothesis.
Yeah, and you can even see the other half of the induction hypothesis on the other side.
Indeed, it can't be necessarily a...
Yeah,
so we don't have to do much, in fact.
yeah, you just do.
I think we just do possibly an under.
No, under won't work
Why not?
because times associates to the left.
Bloody hell.
So that the times on the left is lined up with the second times on the right. And that's a bit awkward at the moment.
So we do have
But
to do
we know times is associative, so we can fix it.
by root.
Yes.
Excellent. So how do we fix this? So we need to fix this part, right?
Yeah. Copy the right-hand side and rebracket it.
Okay. Copy the right-hand side. What's the copy?
Squiggly C.
Squiggly. It's like using a French keyboard.
Yeah.
Sorry.
That's
Sorry, where do I have to bracket now? Like this?
yeah, you need to make sure that it's that star is at the top. Yeah.
And top. And now we are at home because we have on the right-hand side of this of the multiplication the induction hypothesis. And on the left-hand side, it's kind of true trivially.
Yeah.
Because it's the same thing. So we can do an under star.
And we're home. So we've got that 2 to the power is not just any old function from numbers to numbers, it's a monoid map from adding to multiplying. And now, with not very long to go, thank goodness, I have the instruction to myself to take a look at the tutorial problem, which would be a whole lot easier if it existed. And but it nearly exists. So I'll see how much I can do. I need to do a share on the Zoom. I need to do a Zoom share. So, oh, hang on.
Never been more on time.
That's the wrong thing. This is last year's. That's a nightmare. It's not what we want. No. And now Zoom is doing the thing where it cats. It does the cat thing.
Stop my computer in case.
Right. Hopefully this will do something. When Marx eventually talks to us. Right. So I've got the first stage lined up for you. I give you plus, I give you substitute, and I'm giving you a new type, which some of you may have seen before. It's the type of bits. And I want to write 0 and 1, but I'm not allowed to because constructors have to begin with a capital letter. So I'm going to use O and I and pretend. O and I for false and true. And then I define the not operator. And I define a bunch of other operations which might be new to you if you don't do CS106, or they might be extremely boring to you if you do, namely and, which says, you know, we want them both to be true, or, which means we want at least one to be true, equals, which does what it says on the tin, and exclusive or, which is true if exactly one input is. All right, so these are 4 binary operations on bits, and the question that I'm posing to you is, first of all, do these operations give you monoids? And are there any other monoids on the bits? Have we found them all? So this is you got to catch them all moment. You're going to find all the monoids on the bits. Okay. So, and I give you a clue as to how to do that. Basically, there's only 2 values, 0 and 1. So once you've decided what you want the neutral element to be, that's 3/4 of the cases covered. Because there's, you got to decide there's 4 combinations of the possible inputs. And once you've chosen the neutral element will be involved in 3 of the 4. So the only choice left you have is what to do in the other one. If that makes sense. So we're going to work it out that way. And once we've done that, the next step is to find all of the monoid maps from adding to the monoids on the bits. What are the interesting monoid maps? And it turns out that there are 4 boring monoid maps. Well, actually 2. No, it's 4. There are 4. So you can always make a monoid map that's really, really boring by sending everything to the neutral element. So the function that's always 0 is a monoid map from adding to adding. It's multiplying by 0. Fine, dull. But the exciting monoid maps take the neutral element, or take something somewhere other than the neutral element. So you've got to find the interesting monoid maps from the adding to the interesting bit monoids. And we'll on the way we'll meet some other things. Right, because some of you may have seen laws that say things like ring any bells? Sorry, not on the camera. My bad. And I should stop sharing. Stop share. Right. Does that ring any bells? If I use, well, it's also the case that not true is false. So now this thing that was given a funny name that you'll struggle to remember called the De Morgan law is only part of a picture, and it's saying nothing other than not is a monoid map from and to or. And you also have the other De Morgan law, which says not of 0 is 1, not of A or B is not A and not B. And again, that's just saying not is a monoid map that goes in the other direction. Now, Augustus De Morgan lived half as long as George Boole, but he did just as much stuff. I have to shut my phone up. George Boole lived for 80 years. Augustus De Morgan lived for 40, but Augustus De Morgan knew that for every fact you know about logic, you get a free fact along with it, because the choice of which of 0 and 1 means false and means true is completely arbitrary. And I like to wind up people that in the Southern Hemisphere, 0 means true and 1 means false. And there is a way to translate from our logic to Australian logic. You just negate all the things. And then and means or means and everything still works. So the fact that negation is not just a function from bits to bits, but a monoid map that switches the roles of and or is extraordinarily useful. And again, it's not anything other. It's not a new idea. It's the same idea as the distributive law. It's the same idea as all of this stuff about 2 to the power. It's the same stuff over and over again. And my plan is to make you sick to death of it. Isn't it? But, you know, it's great that there'll be almost no ideas all over and over again. I'll teach you a few tricks. They'll be very useful. And all of a sudden, the world will look different to you. All right, folks, can we have, I'll knock it off for there today, because I'm going to get on my way to Livy Tower 210. Can we have 1 minute papers in the box, please? Right, cheerio, YouTube.